In this video, we'll talk about Newton's 3 laws for force. And force, of course, is important in the universe. The gravitational force, creating orbits, and other actions going on too with gravity and people on planets. But let's go ahead and just do the basic laws, not worry about astronomy applications in this video. So our first law, Newton's first law, says that if the net force on an object is 0, the velocity will be constant. So the velocity being constant means the speed is constant, the meters per second, and the direction is constant. So we're going to take a brick here, a 3-kilogram brick. We're looking down on the top of this brick, and it's traveling on frictionless ice. That's a common physics medium. No friction with the brick on the ice, traveling at 1.3 meters per second towards the east. And there are 2 strings attached to the brick. String number 1, pulling horizontally here. Again, we're looking on the top view. So from down on the top, we have the string horizontally towards the south with 6 newtons of tension in the string. And a second string pulling to the north on the brick with 6 newtons of force. So what's our velocity after this brick moves for 6 seconds or 10 seconds or 20 seconds? Well, if we take a look at the situation, there are only 2 forces in the horizontal direction. That's the string 1 and string 2. They have the same magnitude, they're opposite directions, they're acting on the same object, acting on the brick. So we're allowed to subtract them, and we come up with 0 net force. Doesn't matter which one of these you call positive, but say the north is positive, then the string to the south would be in the negative direction, and would, when we add those 2 forces, they would add to 0. There are other forces acting on the brick in the vertical direction. The brick has a weight. There's a gravitational force pulling the brick towards the center of the earth, but the ice has a normal force going upward. We're not considering those forces here. Don't need to. They do exist. But with 0 net force, the velocity is going to be constant. So after it moves for 6 seconds, we still have 1.3 meters per second of the speed to the east. After 10 seconds, we would still have 1.3 meters per second to the east. These 2 forces balance each other. The net force is 0 in this horizontal direction, and the vertical direction as well. The net force is 0, but we maintain this velocity because the net force is 0. So let's go a little more complicated. Suppose that the second string breaks. So there's no longer the 6 newtons pulling to the north. What's the acceleration of the brick? Well, now there is a net force. The F equals ma. The F here is the net force acting on the object, the net external force. Don't worry about internal forces of the molecules in the brick. The mass is the mass that is in motion or system that we're considering, and A is the acceleration. Well, we only have 1 string, 6 newtons, so the force is 6 newtons, and that force is to the south. We have a brick with a mass of 3 kilograms, and then we are calculating the value for the acceleration, so we divide both sides by 3 kilograms. When we divide newtons by kilograms, we get meters per second squared, the units of acceleration, and 6 divided by 3 is obviously 2 meters per second squared. This is incomplete. This is the magnitude of the acceleration. What's the direction of the acceleration? The acceleration always has the same direction as the net force, though this is to the south. And that's our acceleration value. Okay, F equals ma. Remember, F is the net force acting on the object. Don't add any forces together that are not acting on the object of interest. In this case, we only have 1 force. So the reason for that is we used string pulling to the north that broke. All right, third law. Force of object 1 on object 2 is equal to the negative of the force of object 2 on object 1. These two forces have the same magnitude. The minus sign just means we change the direction. Notice that the force is acting on different objects. So we're continuing with the second law example. There's only one string acting on our brick. So we have a string with a tension of 6 newtons in it, pulling off to the south. We're moving 1.3 meters per second to the east. This string pulls on the brick. So this could be our left side here. There is a force of the string on the brick, 6 newtons to the south. What's the force of the brick on the string? Well, it's going to be the same magnitude, and this force, the brick, I'll go ahead and write it out here. Brick pulls on the string with 6 newtons of force to the north. So right here, if you consider this contact point, the string is pulling to the south with 6 newtons on the brick. The brick is pulling north with 6 newtons of force on the string. So that's Newton's third law. There's an equal magnitude but opposite direction force. It's very, very, very important that you realize these forces act on different objects. This 6 newtons of force of the string on the brick and the 6 newtons of force of the brick on the string cannot be added. They cannot be added. They act on different objects. The string is acting on the brick is acting on the string. The net force is not 0 here. The net force is not 0. The string is pulling on the brick, and we have its acceleration caused by virtue of the second law. So Newton's third law, the forces always come in pairs. The forces have the same magnitude, they have opposite directions, and they act on different objects. So please ask your instructor if you have questions on Newton's three laws of force.